Okay, here's the first half of Chapter 14, which is a quick look at acids and bases and a process known as titration. The next video, the second half, we'll take a look at the pH scale. Okay, acids and bases, what are they? Well, they're ionic compounds, so again, you have a cation hooked up with an anion. And in the case of an acid, the cation is always H+, which we refer to as the proton. So a typical acid, you've seen this before, things like hydrochloric acid, HCl. Although we write it as if it's one thing, when it's in a solution it exists as H+ and Cl-, and those two chemical species are really quite separate. They're not really connected to each other. Nitric acid, another acid, HNO3. In solution it's going to exist as H+ and NO3-. So ionic compounds in which the positive half is the proton, H+. That would be an acid. Now, bases. Bases are ionic compounds where the anion, the negative half, is always the same thing. It's always hydroxide. So some typical bases would be things like, say, potassium hydroxide. It's like any other ionic compound, the metal is carrying the positive charge. So you have your K+1 OH. That's the hydroxide anion. There you go. So, ionic compound in which the negative half is the hydroxide ion, that's a base. Sodium hydroxide, very common laboratory reagent, sodium hydroxide. The positive half is the sodium ion. The negative half is the hydroxide ion. So acids and bases. Now, the thing you got to know about these is the way they react with each other. Keep in mind they're opposites. They're complete opposites of each other. An acid is considered to be the opposite of a base. When opposites get together, they destroy each other. So an acid plus a base will react to produce water and a salt. And you might recall from our previous discussion, the acid, of course, is this HCl is kicking out H+, Cl-. This KOH is K+, OH-. When they react, how do they end up making water? Oh, the protons hook up with the hydroxide ions and they end up making water. So that's where the water comes from. The protons react with the hydroxide ions. Now keep in mind, each of these compounds individually is quite corrosive, quite dangerous. You know, a good strong acid kicks out a lot of protons. That will burn your skin, put holes in your teeth, dissolve metals. That guy is a pretty reactive chemical species. A good strong base, potassium hydroxide. Hey, that hydroxide will take your skin off. That will eat your skin right off of you. It'll turn you into soap. That's how you make soap. Animal fat and hydroxide ions produce soap. So individually these two things are quite nasty, but they're opposites. You put them together, they neutralize each other, and they produce water. That's why it's referred to as an acid-base neutralization. Those two nasty things destroy each other. Now, an acid plus a base always gives you water and a salt. Who's the salt? Oh, anything that didn't turn into the water. Notice the two species that didn't end up being in the water? Those two things end up being your salt. So if you were to finish this one out here, your salt is going to be composed of sodium combining with sulfate. You'll end up with Na2SO4 as your salt. Your other product, of course, is water. And of course, to make this one balance, turns out you end up making 2 moles of water. You have to use 2 moles of sodium hydroxide. Now it's a balanced reaction. Okay, that's a quick review of acid-base reactions. Now, we're going to talk about a laboratory procedure that's quite common. It's referred to as a titration. If you take some more chemistry, Gen Chem 1, Gen Chem 2, you're going to see quite a few titration problems. You'll do a few titrations in the lab. The way a titration works, you're essentially measuring the concentration of an acid, and you do that by adding a base to it, and you neutralize one with the other. You're measuring the concentration of one against the concentration of the other. Quick look from the book here. This is how a typical titration is set up. Zoom out. That's as far as I can zoom out. Okay. Let's do this. So in a titration, you have a long glass tube referred to as a burette. And that burette in this instance is filled with your base, your hydroxide. Do you notice the OH? These little guys here, OH, those are your hydroxides. Your acid is, in the flask here, they're showing the acid as these little gray spheres, that's H+. So, H+, that's your acid. OH-, that's your base. And in the process of a titration, you start with your acid, you add a little bit of the base. Hey, what's going to happen? This guy, the OH, as soon as it hits this solution, is going to hook up with that H+, and it's going to make a water molecule. So after you add a little bit of the base, notice these water molecules. That's H2O, that's water. There's another water. Notice how we have fewer protons. We started off with 1, 2, 3, 4, 5 protons. Now we only have 3 protons. You keep adding the base. Eventually you get to a situation where all of these protons are gone. As soon as all the protons are gone, boom, the solution turns pink. It's like somebody threw a light switch. It's kind of interesting when you first do one. It's kind of impressive. Quite often, the addition of half a drop of extra base from here makes the solution go from colorless to pink. The reason it turns pink is because we've added what's called an indicator to the solution. So that's why it turns pink. Now, the idea here in a titration is when you hit what's called the end point, sometimes it's also called the equivalence point. So you hit that equivalence point or end point. At that point, you can say the number of protons you started with here equals the number of hydroxides that came out of here. So if you know the exact concentration of your base, and you're able to measure the volume of the base, you can find moles of the base. And moles of the base will be equal to moles of the acid that you started with. So you're measuring one chemical by reacting it with another chemical. Real quick, let's try and run you through some calculations. Here's a quick example. It says you're doing a titration and 35 milliliters of 0.2 molar sodium hydroxide is used to reach the end point in the analysis of a 2 milliliter sample of sulfuric acid. Now, the overall reaction for this, here's your acid, H2SO4, Here's your base, your sodium hydroxide. Any titration problem we give you here, we'll give you the balanced equation. We'll give you the balanced reaction. You end up making Na2SO4, sodium sulfate, and of course you end up making 2 moles of water. Hey guys, quick heads up. We can make titration problems look incredibly complicated. We can go on and on explaining different chemical concepts and stuff in a titration problem. At the end of a day, all titration problems come down to 3 numbers. You've got a volume for your acid, so we have 2.00 milliliters of our acid. We've got a volume for our base, 35.00 milliliters. We know the molarity, we know the concentration of that base. We were given that 0.200 molar. If you have a titration problem and you're lost, write the numbers that go with the chemical. What you're doing in a titration problem, you're looking for a 4th number. What is the molarity of the sulfuric acid? That's a question mark. What is the molarity of that acid? And if you outline it, suddenly it's really easy to work. What do you do with this stuff? Well, see, you got a volume, you've got a molarity. You can find moles, right? Because you know that 0.200 molar translates to 0.200 moles per liter. That's what that big capital M means. Since we're working with the units of milliliters, I'll take this conversion factor and I'll change it just a little bit. Instead of calling it moles per liter, I'll say it's 0.200 moles per 1,000 milliliters. Because after all, 1 liter is exactly the same thing as 1,000 milliliters. So these are 2 conversion factors that you can use that we took from here. I like using this one myself because our units here are milliliters. So what are we going to do with this? Oh, I got a volume, I got a molarity, I'm going to find moles. So the first step in this is to say 35.00 milliliters, 0.200 moles of sodium hydroxide per 1,000 milliliters. And if we run that through our calculator, we end up with that many moles of sodium hydroxide. What that number represents is, in this procedure, how many moles of the sodium hydroxide came out of the burette. So if we know moles of sodium hydroxide, we can find moles of the acid. And how do we relate the two? Oh, a mole to mole ratio. There's 1 mole of the sulfuric acid for every 2 moles of the sodium hydroxide. So 1 H2SO4 per 2 sodium hydroxide. So that ratio there, that's a conversion factor that we just ripped off of this here balanced equation. So the second step is to convert sodium hydroxide into sulfuric acid. We've got our 0.0007000 moles of sodium hydroxide. Let's say there's 1 sulfuric acid for every 2 sodium hydroxide. That's going to give us 0.00350 moles of sulfuric acid. Hey, that's how many moles of sulfuric acid we started with in the beaker here. What the problem's asking is, what's the concentration of sulfuric acid here? Oh, hey, that many moles of sulfuric acid came from a 2 milliliter sample, right? So the third step here is to simply find the molarity of our acid. And by definition, molarity is moles of the acid, moles of the H2SO4, divided by liters. Oh, it's going to be this number for the top number. 0.00350 moles of H2SO4. How many liters? Well, we used 2 milliliters. That's 0.00200 liters. The molarity of the acid is 1.75 molar. And that's a titration. Again, it's used to analyze the concentration of something, typically an acid or a base. So you want to know the molarity of your acid, you take a little sample of it, you run it through this procedure, you take measurements, you do all these calculations, boom, you know your molarity. So a titration is a procedure used to determine a concentration. Real quick, in a hospital setting, occasionally you'll hear the word titer. Like you might hear somebody say, hey, what's the patient's antibody titer? Titer in the medical setting has come to mean the same thing as concentration. So when they say, what's the antibody titer? They're asking, what's the concentration of antibodies in the patient? Why would they use a word like titer? Oh, every doctor has to take chemistry. Chemistry classes, we stress these titrations that you use to determine a concentration. So the word titer has come to be synonymous with concentration, because how do you determine a concentration? Oh, you do a titration. So titer, concentration, they mean the same thing basically. Hey guys, on the flip side of this, it kind of diagrams that problem we just worked. It shows you what it would look like in the lab. You got the burette, you added this much hydroxide to this much, or this much of your hydroxide to that much of the acid. So hopefully that helps. There's also another problem for you to work. A practice problem, an additional practice problem in the packet of notes. And here's the answer key to that one. So it's just like the last one. It's walking you through the titration of a phosphoric acid sample. I'm not going to work this on the video, but if you need a little bit more practice, the notes are there. The answer key is in the notes. Those are titration problems. You're going to see them over and over and over again if you take chemistry. And the thing to remember, it's just 3 numbers. You always know 3 numbers, and you're looking for the 4th number. So practice your titration problems. The next video is going to go into the pH scale. You all take care.